Last section we talked about the compound interest formula, capital A equals lowercase a times the quantity of 1 plus r divided by n to the nt power. R stood for rate, n stood for the number of times per year compounded, t was time, small a was the principal, and large A was the amount that it would be worth after a specific rate in a number of years. Well, let's suppose that we have $1 invested at 100% interest for 1 year. What would be the amount in the account after 1 year if we just compounded annually or one time per year? So we could figure that out by taking the $1 per year at 1 plus, the rate is 100%, so as a decimal, 100% is just 1.00 or 1, divided by, if we're going annually, the number of times a year would be 1, to the 1 times 1 power. So yes, there are lots of 1s there. So annually, what would be the account worth? So we would take 1 times 1 plus 1 over 1 is 2, to the 1 times 1 power is 1, and we would just get $2. So annually, our account would be worth $2. But let's suppose that we weren't doing it annually. Let's suppose that we were doing it monthly. So monthly, all we would do is we would need to change the number of times per year to 12. So I would change both of the ends to 12. So it would be 12 times 1. So I would change that to a 12. And the n here would be changed to a 12. And then, so we would have 1 plus 1 and 1/12 would be 1 and 1/12. To the 12th power. And when you would do that, you would get about 2.6130. So doing it monthly, it would be worth about $2.6130. And we can continue to do this for as many times per year if we want. We could do it weekly, and your answer would be 2.6930. We could do it daily, and your answer would be 2.7146. And we can do it even, let's just skip to minutely. Minutely would be 525,600 times per year. In minutely, you would get 2.71828. So anyway, the whole point of this exercise is to show you that even though you're compounded it many, many more times per year, notice that it is not earning that much more interest per year. I mean, we're just getting a few extra pennies when it goes from monthly to weekly to daily to when minutely, from daily to minutely, it's actually fractions of pennies. So it's actually approaching a very special number, and that number is called E, which is referred to as the natural number. The reason it's called the natural number is because it exists in nature. It is often used in population growths because populations just don't automatically grow at the end of the year and suddenly, boom, we get a bunch of new animals or a bunch of new people. There's a gradual growth throughout the year. So the natural number is approximately equal to 2.71882828, and no, it doesn't repeat. Then it suddenly goes to 459, which doesn't, your calculator doesn't show the 459 when you find the E button on your calculator, which is usually you have to shift to get to it. It's like pi. It goes forever. There has been no end found to E. There's been no pattern. to it. It just continues forever, just like pi, and referred to as the natural number. So what we're going to be doing today is to be discussing how to solve equations involving E, where we would apply E in real-world situations, and talk about logs of base E. Since we're going to have to solve equations with variables that might be in the exponents with E, that's why we have to use logarithms. So you won't see a log of base E written like this. You won't see it written as log of base E. It's actually written as ln. E was discovered by a Frenchman. His name was Euler, and this is how you spell it, E-U-L-E-R. Presumably, he named it the natural number after himself, which is why it's E, I suppose, for the first name in his, or letter in his name. So ln, being a Frenchman, is just like in Spanish, you would have the noun before the adjective, so ln likely stands for logarithm de naturel. I don't speak French, but I'm going to guess that's what it's all about. So, and whenever you see ln, we're actually talking about log of base E. So we can do everything that we've done with logarithms with natural logs as well. So example 1 says write each exponential equation in logarithmic form. So e to the x power b equals 8. So since this is a log that we're trying to write it as, the base of the exponent is e, so it would be a log of base e of 8 equals the exponent, which is x. Again, you would not write it as log base e. You wouldn't write it as log. You write it as ln. So it's ln of 8 equals x. On part B, it's e to the 5th power equals x. So if I want to write this as a natural log, since we have a base of e, it would be ln of x equals the exponent, which is 5. Example 2 is to write the logarithms as exponential equations. So since it is a natural log, we're dealing with base e, so this would be base e, the exponent is 0.7741 equals x. And then part B, ln of 10 equals x, so it would be e to the x power equals 10. Just like we can do it with common logs, we can rewrite natural logs as a single logarithm. So if we have 3 ln of 10 minus the ln of 8, so where did the 3 come from before it was expanded into 2 logarithms? Well, it was originally an exponent, so we can move that back. So the 3 gets moved back. So this would be as a single logarithm, ln of 10 to the 3rd power. Since we're subtracting another natural logarithm, remember, subtraction of logarithms equates to being the division of a single logarithm, so we could divide that by 8. 10 to the 3rd power is 1,000 over 8, and 1,000 divided by 8 is 125. So the original problem, 3 times the ln of 10 minus the ln of 8, could be rewritten as a single log as ln of 125. Part B, everything is addition there. So we're going to rewrite this using a series of multiplication. There is a 2 in front of the ln in the second part of the expression. So I'll go ahead and move that back to the exponent that originally was. So as a single log, this would be ln of 40 times 1/2 squared times x. And when I simplify 40 times 1/2 squared times x, so 40 times 1/2 times 1/2 is 10x. So all of that could be simplified to the single natural log ln of 10x. When solving exponential equations, remember it's often easier to do that by changing them to logarithmic equations. Because the natural base and the natural log are inverse functions, they can be used to undo or eliminate each other. What that literally means is that if you take the natural log of the natural number, they cancels each other out. The reason for that is because what is the natural log of the natural number? Well, that would literally mean you're trying to find e to what power equals e. Well, e what power equals e? Well, that would have to be to the first power. And when you take the ln of e, you would have the ln of e would literally equal 1. And then if you have 1 times something in the equation, you wouldn't need the 1 anymore. So that's why it seems like the ln and e cancel each other out. So the way it would work is on example 4 is solve for e to the negative 2x power minus 5 equals 3. So I'm going to get the e and its exponent by itself first. So I can do that by adding 5 to both sides. So that would be 4e to the negative 2x power equals 8. Then I can divide by 4. So that's e to the negative 2x power equals 2. So I'm trying to solve for x. X is in the exponent, and when that happens, we should use a logarithm of both sides. A natural log works, quite frankly, naturally well with the natural number. So I'm going to do a natural log of both sides of the equation. So I'm going to take ln of both sides. And by doing that, the ln and the e eliminate each other, leaving us just with negative 2x equals the ln of 2. And then to solve for x, I would divide by negative 2. So the answer for x would be whatever the ln of 2 divided by negative 2 is. So then you would go to your calculator, locate the ln button. So ln of 2, make sure you close the parentheses if you have a calculator that opens parentheses like that. And then divided by negative 2 would give you approximately equal to negative 0.3466. Going to have to round that 5 in the 4th position up to a 6. And that's your answer. On 4a, it's going to be solved very similarly. Spit that word out. Add 12 to both sides. So 3e to the 4x power equals 27. Divide by 3. So e to the 4x power equals 9. And now we can do a natural log of both sides to cancel out that e. So that gives me 4x equals the ln of 9. Divide by 4. And to the 4 decimal places, 0.5493.